Hello, ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be talking about a brief introduction to cyclohexane. And so before we go any further, we have to actually probably show you what cyclohexane looks like and what its formula would be. So cyclohexane is C6H12, and it can be represented in line structure form simply as a nice little hexagon. So we're used to drawing our line structure something like this when we deal with rings. Remember, cyclobutane was like a square, and then cyclopentane was a pentagon. So of course we use a hexagon to represent cyclohexane. Makes sense. The only problem is that because technically if you were to build this structure and add your hydrogens, it's a three-dimensional structure. It has several different forms that it can take, and we call those conformations, okay? So here is a 3D structure. You can see it at the bottom. And notice that it's not entirely flat. There are some areas which are going down and some areas that are going up. And so again, if you were to push on one of these carbons and push it down, then this one would pop up then. And so you can picture that in a three-dimensional structure like cyclohexane, you could end up with some very different looking geometric shapes, even though it's something as simple as just 6 carbons in a ring. All right, so let's talk about those conformations because they become extremely important. So what are those major conformations? Okay, you're going to need to draw these and pretty much know what they are. So the first one is called chair form, and it gets its name because it kind of looks like, as you can see, a chair. Okay, this is something that you'll commonly see in structures that have rings, but we haven't really gotten a chance to talk about it. When you see like a bolded line, that normally means that it's coming out towards you. So this is actually the front of the structure, and it's poking up, but it's not just poking up, it's poking out, so that it's actually kind of like sticking out. If we had like a, if you were able to see this in 3D, this would be sticking out towards you, okay? This is also a chair structure. It's just the exact opposite, okay? So now this is coming out, and so it's on the opposite side. So notice that the chair structure just has two forms, and it's just the direction the chair is facing. Is it facing up and to the left, or is it facing up and to the right? Then we have the half chair. Okay, this one's harder to picture, and it looks way more like an actual chair. So sometimes people get confused because they're like, why is this called the half chair when I think this looks more like a chair? Well, the half chair structure is the exact same kind of thing, except now notice that we have like a little bit more of a kink facing up, and then this is coming out. The boat structure gets its name because it looks like a boat. That's when both sides are pointing upwards. And then you have the twist boat, which is the most complicated looking one, and you kind of have to picture this is coming out towards you, and now the line behind it is going straight back. Okay, so that means that if you were to look at this from behind, it looks like it's kind of actually twisted. And just like the chair and half chair, there are two forms of that. So what's the big deal? Okay, well, chair structure looks like this three-dimensionally. Okay, and so you can see the hydrogens are the most important part of any structure that you're going to be looking at. Okay, because remember, hydrogens do not want to be near each other because they're going to start to repel each other. And so chair structure wise, this is kind of what that looks like. All right, and so that's how we draw it. And so you can picture the 3D structure and where this 2D version of it came from. It's pretty obvious how that works. Okay, here's another one. Here's the half chair. Okay, the half chair, you can see again that this side is pointing up. Okay, and again, the hydrogens are the most important part to picture when you're dealing with that. And again, you can see that it's pointing up like this. That's the half chair structure. Okay, boat. The boat structure looks like this. Again, notice how symmetrical the boat structure looks. Okay, that's our representation in 2 dimensions of it. And then the one that was the hardest one to picture will be a little bit more obvious when you see the 3D structure. This is the twist chair. So again, you can picture that, even if this is the front, you can see the back is twisted and now it's going down at an angle. And so that's the reason why we kind of represent it using this shape here at the bottom. All right, so why do these different conformations matter? Okay, that's the important part. Well, I'm going to ask you this. Can you predict which of those conformations would have the most energy or the least energy, okay? So take a look at these. You can pause the video if you want, but I want you to take a guess. So make a prediction as to which of these 4 different possibilities would give you or have the least energy and which would have the most. All right, let's get rid of them. It looks something like this. Okay, so the chair conformation is the one that has the least resistance and the least energy. Okay, so why? If you really think about it, okay, think about like the way that the carbons would have to like be situated and where the hydrogens are located. Okay, remember these are all tetrahedral technically. Every single carbon here is a tetrahedral. Geometry. So it wants to have a 109.5 degree angle. And this structure gives it about as close to that 109.5 degree angle without actually straining any of the bonds. Okay, the one that has the most strain, you might think it would be the twisted boat, okay, but actually it's not. The most twisted one is actually a half chair structure. And the reason why is because now you're putting things so close to each other and those hydrogens are really going to interact and things are really strained, okay? If we're going in order, okay, the twist boat is technically a little bit less energy, or sorry, well, I guess I should say more energy. The chair structure has the least. Twist boat has the second least. Okay, I guess that's probably not the best way of saying that. Boat has a little bit more than the twist boat, and you can picture again those hydrogens are really interacting with each other in a boat formation. But again, without a doubt, the half chair is the winner here. It has the most energy. In case you're wondering what these units are, the units aren't important, okay? Technically, it's giving us like relative energy, basically, as a unit of measurement, okay? And so you can picture this, though, okay? If you had cyclohexane floating around inside of a solution or something, okay, it could be in any one of these conformations, and it can switch in and out of them all of the time. So it can go from chair, and then some of those bonds can move, and then it could be half chair, and then it can be twist boat, and then it can be boat, twist boat, half chair, chair. It can go through every single conformation while it's sitting in solution, okay? And again, that's really important. So I'm going to end with this, okay? Based on the energy diagram you just saw on the last slide, can you predict which of those conformations would have higher physical properties, okay? Because technically each one of those conformations has slightly different physical properties, which is why it's important to know about the conformations that we have for cyclohexane. So can you predict which ones would have a higher melting point or boiling point or some other physical property like that, okay? So I want you to think about that. We're going to talk about it in class. We're going to, again, go over what your predictions might be and see whether or not you're right. But if you have any questions, please feel free to contact me. And yeah, so that's pretty much it.